Hello, my name is Cameron Riordan, and today I'm going to be talking about the evolution of gas exchange and osmoregulation in vertebrates. These two systems were essential in helping animals successfully move from water to land, and we're going to show how these systems have evolved across different clades of vertebrates. Starting with Epsilogetids and Tiktaalik, which is inside the group of Eplostegus. And these were lobe-finned fish that were already had that already had developed some adaptations that foreshadowed that they would be able to live life on land. For example, the Tiktaalik had both gills and lungs. It could raise its head above the water to gulp air, and this showed an early sign of lung-based gas exchange, and it also allowed them to survive in oxygen-poor water. Next, we'll look at the Acanthogena and Ichthyostega, and these were early tetrapods, and these animals already had fully formed limbs, but were still fully aquatic. They had internal gills, but they also had primitive lungs, so they could breathe air too. Like a lot of amphibians, they also were able to do cutaneous respiration. And then following that, we have the reptilian morphs. So these were more land adapted than amphibians. They had better lungs, which were better suited for drier environments. And they also were able to develop much more efficient kidneys, which were able to help them conserve water. And these traits were early steps to becoming fully separated from aquatic environments. And then moving on to amphibians, such as frogs and salamanders, they have a dual system. So they breathe through their lungs, but they also rely on cutaneous respiration, obviously, especially when they're underwater. And for the osmoregulation, amphibians have issues because they have permeable skin, and in freshwater, they actively absorb ions, and that causes them to produce a lot of dilute urine. And when they become adults, it makes it so that the kidneys play a really large role. Then we have the amniotes, and these were previously tetrapods that had evolved into amniotes, and they developed watertight skin with keratin and internal lungs. So they had a very large surface area. They also evolved having amniotic eggs, which meant they didn't need to use the water for reproduction anymore. And for osmoregulation, the amniotes evolved more efficient kidneys, which gave them the ability to excrete nitrogen as uric acid or urea, which would in turn reduce water loss. And then we have one of my favorites, the turtles. The turtles show a lot of diversity in gas exchange because we have some freshwater turtles that can breathe through their cloaca, which is an internal structure that's located by the rear. And this is especially useful for them during winter hibernation when they're underwater. And for the osmoregulation, many turtles use salt glands to reabsorb water into their cloaca, which helps them conserve it when they're on land as well. And then we have squamata and serpents, which is lizards and snakes. And these animals are highly adapted to dry environments. Most of them use lungs for breathing, but snakes are often able to reduce just to one lung so that they're able to save space. And to avoid water loss, they excrete uric acid instead of urea in their bladder. It's highly keratinized. So some are even able to reabsorb water from the cloaca or the bladder. And then to summarize, we were able to see a shift from gills and passive diffusion in aquatic environments to lungs and advanced kidneys, and that was able to help support um, life on land. And we saw how the transition occurred throughout the different clades, which was able to show us how important gas exchange and osmoregulation was in the evolution of vertebrates. Thank you.